The stats class, I figure I have some stats. The most important thing up here is this bottom sentence. Two things. If you have questions, what was I looking for? What was I supposed to know? What didn't I? Take a look at the key. It was posted to our Canvas page, as is the review for the final exam. And secondly, come talk to me. Come talk to my office hours. And we can figure out what's going to happen next. I thoroughly expect everyone to pass this course. None of you are in the position where you need, 117 on the final to get a passing grade. So everybody's going to pass. Meanwhile, when we were talking on Monday about our two-factor ANOVA, we specifically mentioned that it was two-factor without replication. What did that mean? Wasn't alone in the room on Monday, so somebody should have written this down somewhere. What was our example at the end of class on Monday about? Two different examples on Monday. Somebody tell me what either of them was about. Or use one of those examples to answer this question. What does it mean to do a two-factor ANOVA without replication? Leo.
It would be like where each factor is observed combinations. Observed once. Each factor combination is observed exactly one time.
Once. So we talked about drivers taking us to hotels. And there were like 4 different choices of hotels and 5 different choices of drivers, but I only had one observation for each driver hotel combination. So when I talk about a two-factor ANOVA being done without replication, I only have one observation for each combination of treatment factors. So what's it mean to do it with replication?
Combinations or certain factors more than once.
I'm actually going to observe all my combinations more than once. Now, ideally, I'd like to make sure I do this for all of them. I'd like to even go more and say that I do the same number of observations for each one. I might not always, but if I do the same number of observations for each combination, we're going to call that balanced data. Now, two-factor ANOVA works even with unbalanced data, but with balanced data, we get a little bit better, a stronger result most of the time. But now I can actually test for one more thing. My data now allows me to look at the effect of the first fact. Which driver I got taking me to a hotel. It allows me to look for which hotel we got, right? But it also allows me to say, hey, is there something particular about this driver at this hotel? Do these factors interact with each other? And if I get a third option of testing, then I end up with 3 sets of null hypotheses and alternate hypotheses. My first hypothesis will be first null hypothesis. Which row I'm in doesn't matter. The effect of the rows are all 0. The second null hypothesis, will be that which column I'm in doesn't matter. The effect of each column is 0. And the third null hypothesis is called the interaction hypothesis. That the combination of row and column does not have an outstanding effect. So now I end up with 3 null hypotheses and 3 alternate hypotheses. That means when I run an ANOVA like this, I'm going to get 3 different values, 3 Fs and 3 P values to go with this. Again, I am not going to do any of these calculations by hand. But an example. Oh, I did forget to write this down. This balanced data idea with all of them being the same, this is often called the full factorial model. And here I'm using the word factorial to emphasize the different factors involved, not factorial like the exclamation point we used in the probability discussion. A market research firm is testing a shampoo. I've got 4 age groups and 4 regions. I give the customers a 10-question questionnaire. How satisfied are you with this product? There are 5, 1 to 5 scale, a Likert scale, with 5 being high, and I get the average score from each person. Problem number 27 on page 441. Here's the data I get. My 4 age groups: youth, college, adult, senior, and my 4 geographical regions: Northeast, Southeast, Midwest, and West. Does this shampoo have a stronger market appeal to one age group or another? Does it have a stronger market appeal in one region or another? Is some combination of region and age group more likely or less likely to use or like this shampoo? Now, all of my groups were 5 people. Great. So this is balanced data. Doesn't have to be. It just happens. All right. I actually have this data in Excel set up just like this. There's our exact same data. Then our in-class example list. The process is exactly the same. I'm going to highlight this data and run through our data analysis a 2-factor ANOVA. Data, this data, data analysis, and it says 2-factor with replication. By laying out this table, rather than just looking at this one list, I think this is an easier way to set up this data, 2-factor with replication. Input range. Notice I am highlighting all of the titles involved. The labels for the rows and the columns, that means I will hit the label selection in my ANOVA box. But it says rows per sample underneath that. I need to tell it how many are in each group so it knows to block that out. There are 5 in each sample group. If I didn't have balanced data, it would treat blanks as blanks, not as zeros. But I still need to make sure I had the same number of rows available in each block. Alpha is 0.05. Let's put the output in a new sheet. Okay, this is a lot of stuff here. But this breakdown by age range, that's by rows, and then within that by region. So I have averages, I have variances within the region. That's what's going to help me look for my interaction effects. But way down at the bottom of all of this, that's where I have the actual ANOVA result itself. This tells me everything I want to know. So now, let's just look at this block. Please notice the way degrees of freedom work. I had 4 rows, so degrees of freedom in the rows is 3 and minus 1. I had 4 columns, degrees of freedom and minus 1. Interaction is 9. Rows minus 1 times columns minus 1 is 3 times 3. So that's exactly our setup. within, that's the samples within each section. That's all the data per. Okay. How do I know what matters and what doesn't?
Do we have alpha?
Yes, alpha is 0.05 again.
So we can check the value.
I can check the p-values against alpha. And if the p-value is what do I do?
If it is less than alpha, we reject the null hypothesis.
Less than alpha, we reject the null hypothesis. The null hypothesis for all three of these is the same. There is no measurable statistical difference based on row or column or interaction. So, for the rows, which in this case is labeled sample, rows, columns, interaction, do the rows matter? The rows are labeled sample, rows, columns, interaction. Does my choice of row matter? Do I keep the null hypothesis? My rows don't matter? Or do I reject it and say my rows matter?
Well, we think we reject the null hypothesis for the.
P-value for the rows is 5.5 times 10 to the negative 14th. That's 0.0000. I got 13 zeros in front of that. Yeah, the rows matter. That's way smaller than 0.05, isn't it? That E negative 14 piece that matters. Now I know that scientific notation is not immediately intuitive to some of you. That's fine. What's the other way I can tell? Rather than look at the p-value.
Do we have the F calc or stuff?
F
Okay.
and F crit. So because I have an F value and an F critical value, when do I reject?
When F is bigger than F grid.
Because that means I'm in that shaded in region in the picture, and this F is 30 something, and my critical value is 2.7. I'm way out there. Not only is this an effect, it's a strong effect. Okay, wait a minute. In this data, what did the rows represent? Which category was that?
The U.
Ages, right? Youth, college, adult, senior. This shampoo is clearly going to be preferred differently by different age groups. There is a strong effect. Which age group you're in matters a lot. And since I'm looking at rows, I really want to look at the row totals. So let's go across the rows. For this last column of information over here on the right, look at the averages there. And I see 3.965, 3.805, 3.55, and 3.37. There's a distinct difference in averages based on which row we are in. There's variance in means in rows. What about columns? Does my choice of column matter? Because this time my p-value 0.6. That's way bigger than 0.05. Look at the F value. My F calculated is 0.05, and my F critical is 2.7. I'm not in the tail. I'm in the main region. No, my choice of column doesn't matter. And if I look at this bottom section right above the ANOVA, we've gone down the columns to look at the averages there. 3.695, 3.69, 3.625, 3.68. They're much closer together. There's very little variation depending on what region I'm in. So in the Northeast, the Southeast, or the West, or the Midwest, wherever they are, that doesn't affect whether they like or don't like this shampoo. Now, is there a particular combination of factors that matters here? Is there an interaction between my rows and my columns? Yes. Because that interaction p-value is 0.0009, smaller than 0.05. So there is something to not just age, not just region, but there's something about the combination of age and region. In this case, DT100 comment. I could go back and I could look at a heat map. And I could say, let's color these 4 boxes, these 4x4 grid up here. These are our actual individual regions, right? Youth in the Northeast, youth in the Southwest, right? Those are my 16 different possible combinations. If I colored them differently based on the value of the average in each one, I might see some that have a substantially larger and some that have a substantially smaller, but it wouldn't be uniform by column. Sorry, it wouldn't be uniform by row because row made a difference. It would be fairly uniform by column, but there might be some bright or dark spots in individual places in. Now this is only 16. If I made this a finer mesh, I might be able to say, let's look at more regions and more age groups. Maybe I could break this down further. Huh. The difference in the p-values, or the difference in the calculated F value, shows me how strong the age-related effect is here. That p-value was tiny. A calculated F was 30-something. That's huge. So age group has a very large effect, but region has a negligible effect. That F value is 0.5. Not the p-value, the F value was 0.5. Yet the p-value is 0.6. 0.65 something? Yeah, 0.649. So basically it's saying, no, this is almost surely randomness. I can visualize the interactions here. Let's choose one of our factors. We could choose region, or we could choose age group. And then we can plot against the other group. This is average by region. But I see 4 different graphs here because those graphs represent the age groups. Youth, college, adult, and senior. And we see how these cross each other. They're not all parallel to each other. There's visibility of my interaction. Those crossing behaviors. If interaction is low, these should all kind of look similar. They should be roughly parallel ideas. Here's the other way. By region against age. So this time, my 4 dots going across, those are the age group averages. And it's by the 4 different regions for the colors. And again, we see these lines cross each other. It looks like they all kind of cross in different places. That's why our interactivity was high. I could go a little further. I could try and now do individual t-tests and say, let's look at regions I think are widely varying. That's where that heat map idea, going back here, and actually coloring these 16, I could say, oh, well, which is the highest average in this whole group? Looks like 4.12 youth in the Southeast. Down here, I got a 3.18 with seniors in the Midwest. There's clearly a difference there, isn't there? If I did a t-test on those two combinations of individual factors, I'd be able to say, oh, here's a strong difference between these two. But I basically said, I know there's a difference here. Questions? So when I look at my actual ANOVA chart and observe those p-values, those S and F critical, that's what's really going to tell me what's going on here, the same way it did in all of our other ANOVA tests. Matter of fact, in all of our hypothesis tests, it was really the p-values every time, right? When I didn't have them, I could look at my calculated, my test value, and my critical value from whatever distribution I was using. Question? How many of you took DT 100 already? That's technically the intro to data course. Technically a prereq for this course, so the rest of you should have. Okay, some more hands. One of your assignments in there asked you to look at hiring algorithms to check for bias in a data algorithm. You were given a data set that had information about an AI score assigned to an applicant based on their years of service, their gender, and their tier of university. I think this was module 7. Yes. Here's the data set. We go back. So, a bunch of applicants, bunch of genders, what kind of school they went to, years of experience, and the score that the AI gave them when it read their resume. The company was accused of being biased in favor of elite universities and against women. How can I check? Well, last semester in data, I did a bunch of t-tests. I did a t-test of AI score, categorical data, I did chi-square, against male. I did AI score against university tier, and I can create histograms. But look over to the right there. There are exactly 36 in each gender category. There are exactly 36 in each gender, in each tier of university. It gets weirder. There are exactly 12 in each possible combination there. I'm going to rearrange this data. $12 male in university tier 1, tier 2, and tier 3. 12 female in tier 1, tier 2, tier 3. 12 non-binary in tier 1, tier 2, tier 3. There's a balanced data set here. This is perfect for me. Rather than saying, let's do separate t-tests against all this stuff, let's do it all at once. No, full factorial ANOVA. Two-factor ANOVA with replication. And when I do that, I want the titles. Rows per sample is 12 this time, rather than 5. Make it bigger still. Does gender affect hiring by this AI score? Is this AI biased by gender? Gender is which one, rows or columns? Rows. Rows is sample up here. Yes or no? Oh, yeah. My F value is 135. My critical value is 3. My p-value is 4.9 times 10 to the negative 29th. There are 28 zeros in front of that. That is way smaller than 0.05. Is it biased by university tier? Because university tier is the columns. So university tier matters. 5.2 times 10 to the negative 7th for p-value. There are 6 zeros in front of that 5. But again, F calculated is 16.8. F critical is 3. I'm way the hell out there in the tails. It is really unlikely for me to say, no, this algorithm is completely unbiased and fair. What gender you are doesn't matter at all. What university you went to doesn't matter at all. So now I know there is a bias. If I am running the company that is using this algorithm, I'm going to get the pantsuit off me. Unless I can actually demonstrate that the claim my lawsuit is making, the suers are making, is false. So now I need to ask, are they right? Am I biased against women?
Well, no, because the interaction from that.
Well, but the gender alone is just the rows, right? Interaction here would be, is there some combination of university and gender? And that p-value is 0.1. So there is no noticeable, statistically significant interaction. But we said which row you were in mattered. So which gender you are matters. So let's look at the gender averages. That's by row. So I want to look over here. Am I biased against women? What do you notice about the average AI scores by gender? Leo?
Looks like the female is the highest one, heard the 76.5 compared to 55.75 and 42.
This AI is actually biased in favor of women, not against women. It is still biased, but my lawsuit is wrong. I'm not biased against women. This AI actually is biased for women. They claim I only take people from high-tier universities. We decided that which university you went to, what tier your university was mattered. That was statistically significant. Am I biased towards high-tier universities, tier 1 universities? I do the same thing now, but I look at the column effects. And again, the highest score average here is in tier 2. So going to a high-power elite university here actually doesn't help you get a higher AI algorithm score. You're not affected in that way. So even though I'll get told my algorithm is biased, it's not biased in the way you guys are claiming in the article. So I've got a perfect defense against your lawsuit. Here's the data. This is the reason that we examine any sort of calculation we're doing. Now, this is an exceptionally unusual one because I said we wrote this AI training algorithm. There was a hiring algorithm at Google that did get removed because it was trained on the hiring for the last 10 years back in 2017 or so. And over 95% of the engineers hired at Google at that point in time were male. So that algorithm was actually biased against women because it thought from its past data that we need men for this job. 95% of the time we hire a man. They used this hiring algorithm. They got sued. They took the hiring algorithm and threw it out. It isn't bias as in this is deliberately out to F somebody over. The bias in that case was completely unconscious. It just perpetuated the same behavior. Banks did this as well for years, but they did it on paper. Your zip code tells me whether or not I can loan you money, because it tells me your likelihood of default. This is absolute BS. But if I gather the statistical data, poorer neighborhoods tend to live in particular zip codes, and their people are more likely to default in that region. Banks called it redlining. Anybody who lived in this area wasn't going to get a mortgage from me at whatever bank of Strasbourg. I don't like that bank. Let's not use them. Again, they were sued because they wouldn't tell you why you got declined for a loan. And the Truth in Lending Act and the Fair and Clear Lending Practices Act requires banks now, these acts, by the way, are less than 20 years old, require banks to disclose the reasoning for declining your loan. And they can't simply say, the algorithm told me. So we have to be able to transparently, clearly explain what happened in this algorithm. By the way, you'll notice I didn't talk about years of service at all, even though in my data, years of experience is one of these options. So does having more experience help me get hired? I'm going to graph years of experience and AI score in a scatter plot. We did that back in chapter 3. It was a long time ago. So I go to insert, and over there's the chart that says XY scatter. Does it look like more years of experience means a higher score? This is now a different relationship. I'm no longer looking at a category versus a number. So my ANOVA told me, hey, if you're in this category, your number might be higher or lower. I'm now looking at two numbers and trying to relate them. This is a different kind of correlation data that I want. And I would like to actually figure out whether or not having more years of experience raises my AI score or not, and if it does, by how much? Because that's something my ANOVA won't tell me. It'll tell me when you're in this category, your score is higher or lower, but it won't tell me how much it moves if I change category. This, I might actually be able to get a numerical relationship here. We did this back in chapter 3. Anybody remember what we did? What are you drawing in the air in front of you, Zach? Okay. Just waving your hand, hoping for magic can happen. I like that. Okay. I want to build some sort of clear relationship between the numerical data here. I need a new test, need a new idea. This idea of correlation in general can now be used to figure out exactly how much each additional year changes my AI score. If I can figure out trends in this data. But that is going to take way more than the 7 minutes I have left today. So that's where we will start Monday. This is the end of chapter 11. This new idea is the start of chapter 12. That means that 2 class periods from now, the homework from chapter 11 is due. That will be Wednesday next week. I will see you all on Monday. Have a wonderful weekend.